Okay, let's look at our sample problem where we apply the rational method to estimate the total the discharge rate of stormwater from a site. So the sample problem we have here is a very simple situation. Our catchment area essentially has a highest elevation here at the northernmost end, lowest elevation here at the southernmost end, and we're assuming that all of our water is flowing downhill from north to south throughout this area. So in other words, the rain will hit this grassy area, flow downhill, then hit the pavement area, flow through that, and we're looking at the discharge right here at the bottom of the catchment. So we're going to estimate stormwater discharge in terms of cubic feet per second. That's the rate of water when the whole site is fully involved. So that's the maximum rate of stormwater being discharged. That will be equal to a C, which is the weighted runoff coefficient. You see here we're given runoff coefficients for the grassy area 0.25 and for the pavement area 0.95. Again, recall that the coefficient is basically a measure of how permeable or an area is. So pavement, obviously almost every bit of the water hits it and runs off, whereas in the grass a lot of the water is absorbed into the soil. So we have a weighted runoff coefficient, again weighted based on the area of the site. We'll do this here in a second. We also want to know estimate the rainfall intensity, how hard is the rain coming down, and we do this here. You see for this problem we're given a 50-year storm. We'll look this up on the weather website on this National Atmospheric Association government website. And we'll look up Southwest Charlottesville for this historical data. And this will also involve using the time of concentration, which I'll show here in a second. And finally, the area. How big is it? How big is the site? So for this, you could do this obviously just for the grassy area, just for the pavement area. Let's make it more complicated, or as complicated as we can get for this problem, and look at it for the entire site. So the first thing we want to do is look at our runoff coefficient. And we want to do a weighted runoff coefficient. So in this case, the C, well first actually let's quickly calculate area. So we have the area for the grass, and that's simply going to be equal to the dimensions, 265 feet times 40 feet, and that's going to be in square feet, and we know that there's 43,560 square feet per acre. So we know that the area of the grass therefore is equal to 0.243 acres. Area for the pavement is similar. It will be 265, the width times 15.5, the depth here, divided by the conversion factor 43,560, and I'll just not include the units in this case, and that will give me a total area for the pavement of 0.094 acres. And then the area total therefore will be equal to 0.337 acres. Now with that, we can next look at what is my weighted runoff coefficient. So my C will be equal to the area of the grass, which is 0.243, divided by my total area, 0.337, times the coefficient for the grass, which is 0.25. And that will be then added to the weighting of the coefficient for the pavement, which will be again 0.094 divided by 0.337, and that'll be multiplied by the coefficient for the pavement, which is that high value of 0.95. So as you see, we're just weighting these coefficients based on the percentage of that area for the whole site. And so our total coefficient here, our composite coefficient, weighted coefficient, in other words, is 0.445. So that's the value that we're going to use here for C in our calculation. Now, let's go to rainfall intensity. rainfall intensity. Now this is where we want to look at this in terms of what is the intensity of rainfall in inches per hour for the site when it's fully involved. So in other words, when all the water that's striking here all the way down to the bottom of the site is all flowing out. And that's where we're going to use our time of concentration. Time of concentration for the grassy area is 10 minutes. So based on different techniques you can do to estimate this, someone has estimated that it takes about 10 minutes for water from here to flow all the way down here to the end of the site. In other words, that's the time it takes for this to be fully involved. So, assuming it takes 10 minutes for the water to get down here, now the time of concentration for the pavement area is 5 minutes. Another 5 minutes to go from here down to here. So our total time of concentration is going to be 10, then 5, 15 minutes. So we know that our time of concentration is 15 minutes. And now we can use that to look at our intensity level from the data. And we also know that we're looking at a 50-year storm. So let's go to this website, which I have right here. And what I'm going to do here is simply choose Virginia. And now let's go by a list of Virginia stations. And I told you here in the problem statement we're looking at for Southwest Charlottesville. So here's Charlottesville, Southwest. So let's use that. And now if I scroll down here, you see it shows up here on the map with that X. That's Charlottesville. And here is the data the historical data that the Weather Service has. Okay. And so again, these are average recurrence interval. So this is 50-year storm right here, and it's giving this to you in inches. So what this is saying is, for this duration of a storm, for this recurrence interval, this is the amount of rainfall that fell during that period. So we're looking for 15 minutes. That's our time of concentration. So in 15 minutes, that's when it's fully involved at the highest rate. And look at the 50-year storm for 15 minutes. I'm sorry for so there's 15 here, 50. So we see here that for a 50-year storm, for 15 minutes, the rainfall was 1.36 inches. So we can go back here to our problem. So we have 1.36 inches in a quarter of an hour. In other words, 15 minutes. And that is the rainfall intensity for a 15-minute period for a 50-year storm. Sorry. All right. So that works out to be, when you divide these numbers, that will give you an intensity of 5.44 inches per hour, which is, you need to have inches per hour to work with the rational method. So now we've got our C value, 0.445. We've got our intensity value, 5.44 inches per hour. So we have C, we have I. All we know is A, acres. And we know that already from up here, for the total acres was 0.337. So now we have all our values. Let's go ahead and estimate our discharge. So it's Q equals C I A. And that means Q is equal to the C value is 0.445 times I, which is 5.44 inches per hour, and then A or acres is 0.337 acres, and this works out to be a value of 0.816 cubic feet per second. So what this is telling us here is that, based on the rational method and based on the assumptions we've made and the data that we've used, we can expect to have 0.816 cubic feet of water every second coming off of this area at this boundary. Okay, so that's an example of applying the rational method here for a simple catchment area.